Hello, everyone. If you guys hear me, can you use the Q&A to let me know? Great, I just got confirmation. Okay, let's get started. So we were talking about 4 concepts of operating systems. The third one was process. So the first one, if you remember, was thread. The second one was address space, and the third one is basically a process. Process is indeed a combination of the 2 previous concepts. A process includes a user space, an address space, and 1 or more threads, as you can see. So I was assuming that you guys know about this. I got a question. I'm just going to clarify this. So the way it works is the operating system is going to provide isolation and protection across processes. But operating systems are doing much less, or even nothing in some cases, when it comes to protecting and isolating threads from each other. So the way it works is all threads in one process, they can all access code, data, and files. Each one of them separately will have its own registers, its own stack, and its own PC, which makes sense because each one of them is potentially running a different piece of code. So they have different active part, if you wish. But the fact that they have their own doesn't mean that other threads within that process cannot see those information. So potentially another thread could mess up with another thread's stack because they can all see each other's stack. The fact that that stack belongs to this thread doesn't mean that it's protected from other threads. But then all of them see the same heap, for instance. So they all share the same heap. So how do we create processes? So the first thing you do to create a process, you create a PCB for it. It's kind of like not very expensive. And then you have to set up page tables and address spaces. We'll talk in a lot. We go deep into details of this later on in the course. And then you copy the data from the parent process that created this process. Usually you fork, for instance. So when you fork, you get exact copy of your parent's memory and IO state, which is inexpensive. Usually there are optimizations that operating systems do in this case. They don't really copy the memory. They just make the parent's memory read-only. So the moment the child process wants to write, to change anything in this memory, they make a copy. So they basically prolong, or yeah, maybe it's not needed. So you really don't want to copy when a process is created. The moment the child process writes, then that's when you make that copy and create 2 separate copies. Yeah, and then you also need to copy the IO state. So we mentioned when we were talking about processes that they include 1 or more threads. So threads are the active parts or components of the process, and the address space is the protected passive part that would keep processes from messing up with each other. Actually, let me get rid of my own. Yep. Okay. So why do we want multiple threads per address space? The main reason for this is performance. So providing isolation and protection will introduce overheads, and that's why multiprocessing is more costly than multithreading. So this is a side note. How do we protect threads if we want to? So so I got a question that is asking what's the difference between active and passive component. Yeah, so as I mentioned, the active component, which is the thread, is the one that is constantly making the changes. Basically, the code that is running, the instructions, the PC is changing, the registers are changing, the stack is changing. And then if there is any change inside the address space, it comes from the thread. It's just a naming, because again, we look at them as threads being actively doing something, and the address space basically protecting processes from each other. That's where the name comes. Now, so let's go to this question. How do we position stacks relative to each other? If you remember, stack was going all the way on top of the address space, virtual address space, and it was growing towards the bottom of address space. Now, if you have multiple of them, how do we position them? Where do we put stacks? So the way it usually works is something like this picture. So you put the stack for the first thread on top, and then the next thread that comes, you put some pre-decided space. You offset by that space, and then you put the stack of the second thread, and so on and so forth. Now, what should be this offset? How much should we put? How much should we reserve for each stack? That's a question that we need to answer. Now, with kernel threads, as we will see later on when we talk about physical and virtual memory, the kernel threads typically are small. We don't want to put much on them. We don't want to, do recursive calls, for instance, inside the kernel, because it could cause damage. We'll again talk about those, but it's usually a small. So the typical in Linux on x86 is 8 kilobyte. With user level threads, it's a little bit less constrained, if you wish, because if you remember here, the address space that we're talking about is a virtual address space. And if you go back and see how much space we have, how much memory we have in a 64-bit system, you see that we have a ton of memory. So we don't really need to be conservative here in how much we give the stack. Usually it is provided by the user. So I believe like something like Java, you can set this as a configurable parameter, that how much stack space each thread gets. So we could leave that to the users of the system. Now, what happens if, let's say, a stack of one thread grows more than what's allocated to that thread? Usually nothing happens, especially if the operating system is not providing any protection between threads. So it's the job of the user of the system, the one who is the programmer that is programming these threads, to make sure that these stacks remain within their allocated budget. Because if not, then they can potentially cause damage. What mechanism could operating system use if it wants to detect such an event? If like, let's say one stack overflows to another stack, how can we detect this? Usually what happens is that you could place guards at the bottom of each stack. So it would be the operating system setting a variable there, like making the value of the last byte of the allocated stack to be some specific thing. And every time you switch between threads, you always check that variable. So if the thread has changed that variable, that means that potentially the stack has gone out of its allocated space. So that's one way we can definitely detect violations. Now, the operating system runs not just one program, it actually runs multiple programs. The way it works is, well, we talked about address space, virtual address space. In reality, our system has physical memory. And this is where the operating system as an illusionist comes into the play. So the way it works is, well, there has to be a mapping between processes, address spaces, and physical address space. So the operating system comes in, allocates a portion of physical memory to each process, and this way it can actually share the system between multiple processes. Then it's the job of operating system to make sure that nobody would get out of their ways to access some other processes data. So I guess we'll talk about this in, again, more details when we start talking about address translation and virtual addresses. If your system has only one CPU, how could you really run multiple processes on that one CPU and give each one of those processes the illusion that they own that CPU and they own the memory of the system and they own all the devices on the system? Well, the way you do this is really by time sharing. So you time share. So you allocate the time available on your CPU to each process. And then with mechanisms that we will talk about, usually a timer, sometimes a process will yield its time. You take away the control from process 1 and you give it back to process 2. You run process 2, and then you again context switch to process 3, and so on and so forth. Now, this has to be transparent to processes. They should not feel like they're being context switched. So the process of context switching, which we'll talk in details in the next lecture, how to implement it, should be transparent to processes. They should just feel like they're running on the process and they own the processor. Sorry, they're running on the processor and they own it. So the way it works usually is that you save the program counter, you save the stack pointer, you save all the other registers that you have. So basically you take a snapshot of the processor's state, you save them in the PCB, and then you load the PC, SP, and all the registers from the new PC that you want to run, from the context switched one, and then you start running it. You just jump to that PC and you continue running wherever you left off from process that is now running. So what triggers this context switching? It could be the timer. So usually you have a hardware timer that will expire. The operating system sets that timer, and then when it expires, the hardware automatically transfers the control to the operating system, which will be the topic of the next concept of operating system. We'll talk about it in a second. It could also, as I mentioned, processes would yield by themselves, or they might need I/O, and that way you basically get an interrupt. I/O so if they are asking for an I/O, they basically almost yielding it until the I/O is ready, and then once the I/O is ready, it interrupts the processor, and that again interrupts the process, goes to the kernel, and then the kernel takes care of the I/O interrupt. Again, we'll see about this in few slides from here. So to make this context switching, some disaster happened here. Give me a sec. Yeah, I think it's fine. Okay, so I got a question. Can you have two processes running simultaneously, each one on its own core? Go there, publish this first, and then answer it. So yes, of course you can. So in a multiprocessor setting, you can run multiple processes at the same time because you have multiple processes. What I was talking about so far, I was just talking about one processor. So what happens if you have only one CPU? Then you still can create that illusion that all of those processes are running at the same time, but under the hood, you're really multiplexing, time multiplexing. Okay, so there are two requirements for time multiplexing to happen really seamlessly. The first one is scheduling. So the operating system has to decide which process should use the CPU at any given time. So this is called scheduling. We're going to have a queue of ready processes or threads that want to execute, and then at any given time, for any reason that either the previous process has yielded or the time has expired, the operating system decides which process to run. Then the next element to successfully time multiplex is protection. You have to divide all the other resources that you have among your processes while keeping them protected from each other, while keeping the operating system protected from them. So first, let's talk about scheduling in a little bit of details. This is going to be a topic of our conversations for multiple lectures. I got another question. So what does it mean when a process says it's so the question is asking, what does it mean when a process says it provides X number of threads, X more than number of cores? I will talk about it. So it's in the slides. We'll touch on that. So if you don't get the answer, I believe it's this lecture. So if you don't get the answer by next lecture, then ask this question again. Let me publish this. Okay, so going back, I'm going to just very briefly, scratching the surface, say what scheduling really mean. So very simply, who's going to use the CPU? That's the decision. If you have multiple CPUs, then who are the threads or processes that are going to use the CPUs? There are criteria that you might want to consider when you make that decision. You might want to be fair between your processes. You might have some real-time guarantees that you have to provide. Maybe your processes or threads or tasks have deadlines that they have to meet. So you have probably to make that into consideration. You might do it for latency. Maybe you are running an audio application or a video application. You don't want to so for those tasks, basically latency is very important. You don't want to lag the video or lag the audio. So there are different criteria to consider. And then usually what happens is that the kernel will maintain a data structure of all the PCBs that are in the system. It looks at the ready queue of these PCBs. It chooses one. So basically next PCB equals select process. This is where the scheduling happens. You make a decision based on your criteria, and then you run it until you get interrupted or whatever, and you do this again and again and again and again, right? And if you don't have any PCB to run, you just idle. In modern modern hardware, you can actually put the processor to sleep, so you can make it as if it's off. It really consumes minimal energy and power. Let's talk a little bit about the ready queue. So what is the ready queue? The ready queue is basically it's a queue of all the processes that are ready to be executed. So all they need is CPU time. I got another question. What does PCB stand for? So this is process control block. Again, it's assumed that you know about it from ECE 252. So process control block basically has all the information about this process, about the user space, address space of this process, about the permissions it has, about the files it has opened, about the memory allocations that the PCB has, about its priorities. So all of those information go to the PCB. Now, what is a ready queue? Ready queue is basically the queue sitting next to this. I mean, not sitting really, but it basically contains all the PCBs of processes that are ready to be executed. Now, when you get executed, and let's say you want I/O, your PCB is going to be moved. So the moment that you start running, your PCB will be removed from ready queue and start running on CPU. So your PCB is removed from ready queue. Now you're running. Let's say you need I/O. So you want to read a file. Your PCB will be moved to the I/O request queue or I/O wait queue. So now you're waiting, your PCB is there waiting for I/O. And once your I/O request is answered and you're again ready to process the data that you wanted, your PCB will be moved back to the ready queue and you're ready again to be scheduled on the CPU to run. You could have other queues in the system for different I/O devices. You could have different queues. For locks, you could have queues. So there are many queues in the system, and if your PCB is not in the ready queue, it should be in one of those other queues in the system. Yeah, so this is basically what I just said. This is one example. So let's say your system has the CPU has its own ready queue, the USB has its ready queue, the disk unit 0 has its ready queue, unit 2 has its own ready queue. Sorry, these are waiting queues. And then Ethernet has its own waiting queue. And this could be the case. So in this case, PCB 9, PCB 6, and PCB 16 are the PCBs that are ready to be executed. So we have the head and tail of the ready queue pointing to these PCBs. A disclaimer: this is not necessarily what happens in all ready queues. So you could have a different data structure. For instance, the current ready queue in Linux has a red-black tree to store and sort the PCBs or TCBs or whatever. So the ready processes or threads. You don't necessarily need to have really a linked list to store them, but this is just, you know, to give you an idea. Now you could have nothing waiting for USB. You could have, again, 2 PCBs waiting for disk to get an answer, and so on and so forth. So as you can see, these don't have you cannot see PCB 9, for instance, in the ready queue and in some other waiting queue. So these are exclusive queues. If you are in one of them, you shouldn't be in any other one of them. Again, this could also happen depending on the implementation of threads and CPUs. You could have a linked list of list of PCBs, and then each one of those PCBs pointing to the TCBs, the threads that are running inside that process. So this could also happen. Or you could just say the operating system doesn't care about PCBs, it just cares about those TCBs and it schedules those TCBs, which is, again, possible. So this is a decision that the operating system makes, the kernel makes, how to address the ready set of instructions to execute by the PCBs, TCBs, whatever. So one thing to note is, again, we're going to get into details of this in a few slides, but just to plant the seed here, context switching between between threads has less overhead than context switching between processes. So let's say that your CPU was running thread number 1 of process number 1. Now it wants to run thread number 2 of process number 1. So the amount of data that has to be prepared for this context switching is minimal. Why? Because this thread is using the same address space as the previous thread. So you only need to just change a few registers. You don't need to touch anything in the memory because it's already there. The heap is there, the process, the code is there, the file descriptors are there. So a lot easier to context switch between threads. Now let's say next thread to run is thread 1 of process 2. In that case, not only you have to change the registers, the stack pointer, the PCB, and such, you also have to change the file descriptors, the pointer to the heap, basically the entire memory stack has to change, because now this new thread has different file descriptors, has different heap, has different code, and such and such. So it has higher overhead to context switch between threads from different processes than context switching between threads within one process. Next is protection. So if you remember, we talked about scheduling. Now we're talking about protection. It's always good to use protection. good news is that operating system will enforce you to use protection. In real life, you should be smart to use protection. I'm not gonna go deeper than that, but now let's talk about why we need to provide protection. We need it for reliability. This concerns protecting the operating system from processes. If one faulty process can cause damage to the operating system, then operating system is compromised. And when operating system is compromised, the entire system is compromised. So the system wouldn't probably be reliable anymore. Security, privacy, fairness, these are other aspects that are very important when you're thinking about protection, because you're actually providing all of those. So I got a question. I'm confused by what you mean by switching threads from different processes. Aren't threads isolated between processes? Okay, let me digest the question. Okay, so first of all, let me publish this. What do I mean by switching threads from different processes? Again, as I mentioned, suppose that you have two processes. Each one of them has two threads. So you have process 1 with 2 threads and process 2 with 2 threads. Now, suppose that you're running the first thread of process 1. And this, let's say this thread needs IO. So it no longer wants to run. You take the TCB of this thread, you put it in the waiting list of IO, and now you want to get another TCB to run, right? So if this new TCB that you want to run is TCB of thread 2 in process 1, your job is not that hard in context switch between the two. So the overhead of the context switching is not that high. However, if the next thread to run is from process number 2, then you have to do a lot more. Why? Because threads within one process share a lot, whereas threads across processes basically share nothing. So you have to bring, for instance, you have to change the file descriptors, you have to change the memory layout. Maybe this new thread's memory is not allocated yet, so you probably have to allocate memory for this new thread. So as you can see, it's much more involved to context switch between threads from different processes than context switching between threads within one process. Again, think about it in a context where you have only one CPU and you have a bunch of processes with bunch of threads. So in that context, I hope that answered the question. Yeah. So I got a nice meme thing. It is very nice. I have a lot of nicer ones coming. Okay. Do modern OSs schedule the process or threads or both? Yeah, it's usually they schedule threads. So at least Linux, I know, it schedules threads. So again, the question was, do modern OSs schedule the processes or threads or both? Yeah, it's usually the unit of allocation is threads, and you're allocating threads. There will be a chart that will make this clear later on. We'll see it. So wait for the for some historical data on this. Okay, let's go back. So the main method that operating systems use to provide protection is basically the translation from virtual to physical address space. That's where the bulk of this protection mechanism comes into picture. This is again just a scratching the surface. We'll have an entire lecture or two about this translation, virtual to physical memory. So just again, we're just seeing everything big picture, and then we'll dive into each one of these topics as the course proceeds. So we have to provide protection of memory, which usually happens by this address translation. We have to protect I/O devices. We definitely don't want to give the direct access to devices to each one of the processes, because they could cause damage. Yeah, one example I usually tell my students is, back in then you had this DVD drive, DVD DVD readers. I don't exactly remember what they were called. So you would press a button, and then it would be like DVD player. Something would come out, and then you put your DVD, and then press the button again. It would go back and start reading the DVD. So there was this really annoying bug or worm. I think it was a virus. So it would just constantly bring that tray out and then put it back without your involvement. So it would access the device, it would make it come out and then go back, and it was so annoying. So you really don't want to give access to devices to processes, because if they're malicious, they could cause damage. And then you have protection when it comes to accessing the processor. Okay, so this is again how the translation works. So we talked about having different address spaces for each process. The reality is that we have a physical address space, physical memory that that all processes are going to use in a multiplex system, time multiplex system. So the way it works is basically the operating system maintains these two translation maps, translation map 1 and translation map 2. So these are controlled by operating system, and they provide a mapping between the virtual address space and physical address space. So the operating system knows where to find each one of these in the physical address space, and also enforces protection on this. If one of the processes want to access an address that is not mapped to it, the operating system can intervene and prevent that instruction to go through. I got a question. What does preemptive mean in this context? Which context? Oh, so when we're talking about process, so basically it means that you're not going to let the process decide when it's going to let go of the CPU, because maybe your process is a malicious one, or maybe there is a mistake. You have a while loop, in an empty while loop in your process, and you get the processor, you start running this while loop, there is no end to it. So when is the operating system going to get the processor back? So that's where you want to preempt threads and processes and enforce that the switching between them. So that's where the preemption comes. So one method for this is to set a timer. When it expires, no matter where you are in your process, the operating system takes the control back and decides who runs again. Maybe there is nobody else in the system, you get the control back again, or maybe there is another thread waiting. So you go back to the ready list and somebody else gets to run. So this is putting it all together, just as an example. You have, we chose Unix processes here for this example. Let's say you have this code that you're running. and you have your memory, you have your I/O state, you have your CPU state. This is the whole thing is basically your process, what it means to have a process. So this is a sequential stream of instructions. These are the resources that you have on your system plus CPU. So your memory, your devices, all of them are represented over there. And then you have the state of CPU that would be stored in the operating system. So this is basically what you have in your TCB, part of what you have in your TCB. Now, in a very primitive form, where each process has only one thread and the system only has one CPU, this is what it looks like. So the operating system has a scheduler that would decide which one of these processes to run. Again, each process only has one thread in this example, so you can just focus on PCBs. You don't need to have any TCB. And at any given time, only one process is running. So the switching overhead here is very high because every context switch happens across processes. And as we talked, switching between processes is very painful and time consuming. CPU state is not that bad because it's a bunch of registers. You can switch them. But what is costly is usually the memory and I/O to switch memory. Maybe in some cases you have evicted one process from memory because you didn't have enough physical memory. Now that you want to run it again, you have to bring all of it back from your disk, and that is very, very time consuming. Process creation is also hard. You have to initiate all the pieces. You have protection, CPU and memory, and sharing overhead is high. Basically, if you want to share data between your processes, you have to dedicate a piece of memory, and then if, let's say, process 1 wants to send a message to process 2, that requires a context switch because you only have one CPU, and that is why sharing actually has high overhead. Now let's step up the game. Let's now consider processes with multiple threads. In this case, each one of those threads has its own CPU state. So we basically took away that CPU state that was in the process. We divided it into 2 for each, or whatever, how many process you have, how many threads you have, and that's basically the picture you see here. Now switching overhead is medium because sometimes it happens between threads, which is really low overhead, and sometimes it happens between processes. So in average or on average, it's medium. Okay, so I got a question here. Without paging, would overhead between thread switching and process switching be comparable? That's a good question. Without paging, yes, on top of my head. So the question says, without paging, would the overhead between thread switching and process switching be comparable? First of all, paging is basically what I mentioned, where you have to evict the memory of one process and bring it back. There is still some stuff there that are expensive, and that would concern the translation map that we talked about. So the thing about that translation map, let me publish this question. This is a very good question. So I would say the answer to this question is still not comparable. It would still be expensive. The reason being that that memory translation, so that mapping that says how virtual addresses are mapped to physical addresses, that map will change when you switch between threads across processes. And that map is stored in memory and is cached in the process, in the processor. So when you context switch, you also have to change that entire map and potentially get rid of all the caches that you have. So basically that's one overhead that you're having in translation. The second overhead is caching data. So when you're running your thread, your process, if there is a data that you constantly use, your processor will cache that data very close to the processor so that the access time comes down. Now, when you switch, maybe the process of switching for the operating system is not that hard, but then when you start running, you don't see your data in the cache. So you have to all the time go to the memory and bring the data back. So overall, when you start running, you see a lot of waiting for your data to come. So in that sense, you still have high overhead, even though you're not, do paging. If you add paging, that would actually be really, really high. Hope that answered the question. It was a really good question. Okay. So here again, going back to this picture, the medium is because it's basically on average. The CPU state is still low, and the memory would depend on, are we switching between threads or are we switching between processes that would introduce, threads within one process or threads across processes that would change the overhead. Thread creation is medium size, exactly for the same reasons. We still have CPU protection. Here, I/O and memory protection, no, because we are not enforcing protection between threads within one process. We still have protection across processes. And sharing overhead is low, again, concerning the threads. So the threads within one process can easily share data with very low overhead because they already share the heap. They can send messages between them using the shared heap. We'll talk about synchronization later on, but from the operating system's point of view, the overhead is low. Now, let's again make it a little bit more interesting and closer to reality. What happens if you have multiple CPUs, multiple cores in your system? In that case, switching overhead becomes really low because now you can run each process potentially on its core, on its own core, dedicated core. So you're not going to context switch between processes, or you're going to context switch much less on average. And the rest of them are the same, sort of. Yeah, so basically you might actually not need to context switch in many cases when you have a lot of CPUs. Okay, now this concerns the question I got earlier about what it means when modern processors say it has, let's say, 4 physical cores and 8 threads. So here is the answer to that question, basically. We're talking about hyperthreading here in this slide. Let's start with the basic one. This is a superscalar architecture. You probably are, those of you who are taking the computer architecture course this fall, you're going to see this. So basically what this means is that on the x-axis here, basically here horizontally, we have a system which can execute 3 instructions at any given time. I got another question. So it says, in systems with multiple cores, is it common to just have one manager core that always runs the OS? That's a very good question. No, it's not. It's not a common theme to have only one, to dedicate only one core to run the kernel. So kernel usually in modern operating systems is itself multi-threaded. So the threads of the kernel could run on any of these processes. Usually what happens is when the system comes up, it only has one core, but then that one core searches for other cores, introduces them. So the system becomes multi-core, and each thread of the operating system can run on each one of those cores. There are operating systems with that architecture where one core is in charge, but that's not common as far as I know. So what is paging? Is that just dividing the memory into finite blocks? So don't worry about paging. That would be later on in the course. I'll talk about paging. So for now, what to consider is that what happens if you don't have enough physical memory to fit all your processes. In that case, you have to evict the memory of one process or two processes to the disk, and later on bring them back when you're running them. So the mere fact of you're basically bringing data back and forth between the disk and memory as you context switch introduces overhead. So again, we'll talk about paging later on. So if you don't know about it, don't worry. Okay, so coming back to this picture here, so vertically here you have time as the time progresses. Horizontally, this means that your processor can execute 3 instructions at the same time. Let's say you have 3 multiplexing units, multiplying units, or 3 adders in your processor in one CPU. So you can actually execute 3 adds at each time. So this is a superscalar architecture. Now, in this picture, some of those blocks are colored and some of them are left empty. This means that you might actually not have enough instructions to run at that particular time. So in this picture, at time 0, you only had 2 instructions to run. And maybe those 2 instructions had dependencies for the second 2 instructions. So the second 2 instructions have to wait. Let's say you wanted to bring data from memory and your memory is slower than your CPU cycles, so you have to wait and then execute these 2, and then wait a little bit, execute these 3, execute these 2, and so on and so forth. So as you can see in this picture, there are a lot of empty spots here. So these are weighted CPU cycles. You could have done something here, but because of the dependencies in your code, you were not able to use those cycles. So one fix to this is multiprocessor architecture. So you could actually have multiple of these. This is actually not a fix, but this speeds up your execution. Now, at the same time, you have 2 processors, so you can run 2 threads. So you can run thread 1 and you can run thread 2. You haven't still solved the problem you had with those empty spots, but your overall speed up has gone up. What you can do to address those empty spots is you can do fine-grained multi-threading. So you can, in a very fine-grained way, multiplex between those threads. So in those cycles, so one cycle run thread 1, one cycle run thread 2, again back to thread 1, thread 2, and so on and so forth. So in this way, you're kind of like using this empty spot here to run thread 2, and you get better use of your CPU cycles, better utilization. The ultimate way of dealing with this is simultaneous multi-threading. So this one, basically, this is a capability that the processor provides in a sense that it actually can run 2 threads at the same time. So instead of just giving me 1 TCB to run, you can give me 2 TCBs. So basically, I have 2 PCs, 2 program counters. So the first program counter points to thread 1, and the second program counter points to thread 2. And at each cycle, I try to fill up all these empty spots. So as long as each one of these threads has instructions for me to run, I can run those instructions. So I'm not multiplexing between them. I'm actually at the same time dequeuing or fetching instructions from each one of these threads. So this achieves the highest levels of utilization. So this is a case where you have one physical core, but that one physical core provides a capability for you to run two different separate processes. That's why they call it in the architecture or hardware realm hyperthreading, or they say you have one physical core and two threads. Do these threads need to be from the same process? No, not really. So again, as I said, we're talking about the hardware. The hardware doesn't really care. It says give me two PCs, two program counters, and basically what it does is it almost all the important registers, you have two copies of them. It's not exactly like you have copied the processor, because they still are sharing these three units here that you had for execution, right? So I haven't made this 3 to 6. You still have limited resources, but I have duplicated my registers so that at the same time I can run two threads. These two threads could be from two different processes, or they could actually be threads of the same process. From the hardware's point of view, it doesn't really matter. Okay, I'm gonna stop here, give you 2-3 minutes, and then we'll continue later. So get up, stretch, and then we'll continue in 2-3 minutes. Okay, I got another question. It says, so you can switch between threads without any context switching overhead? Yes, exactly. So you're basically the only overhead here. There's no context switching overhead. The overhead is basically those two threads sharing the same 3 units of processor. So that's the only contention, that I would call it contention between those threads. Okay, another question. In SMT, by duplicating register state, does that mean it has to store all the process information as well if the two threads are from different processes? So this is the job of, if I understand your question correctly, so it's the job of the operating systems to set those registers. So in the next slide, we'll see how just in a picture, we'll see. But then the operating system decides to, let's say, run these two threads on these two virtual CPUs, let's call them. I think that's what they're called. So you have a physical core and then virtual cores if you have SMT. So operating system decides to run two threads. So it will set all those registers to point to where they have to point. So the PCs to point to the codes that have to be run, the stack pointers to the stacks of these two threads. So it's the job of the operating system to set those registers. And then if you do context switching, you have to save all the registers for each one of those threads in their TCBs and then do context switching. Again, job of the operating system. Okay, let's continue. I'm a little bit behind, so I'm going to speed up a little bit. If you want to read more about this, this is a link. Definitely take a look. So this is now the picture of how it looks when you have hyperthreading. I got another question. So why does the register state need to be duplicated? Again, because if you want to fetch, for instance, 2 instructions from 2 different threads, you need to have 2 PCs. If each one of those threads is going to run call a function, you need 2 stack pointers. If you have only one, then it would be the fine-grained one that you're just at each time you're basically doing one of them. But in order to do both of them at the same time, we really need to duplicate your registers. Another question, what the limitation on having more than 2 virtual cores per physical core? So the limitation is basically as you, I'm going to publish the question for those who want to see it. So the limitation is basically the fact that there is a contention now on the resources that you have on your processor. So let's say you have 3 adders. So if you have a superscalar of width 3, then if you have 4 threads, then there will be contention on which one of threads to run. So it would add overhead for the hardware to decide which one of these threads should be executing or should be running, and so on and so forth. So the contention on the resources would go up because you're only duplicating the registers. You're not really duplicating all the resources that your processor has. So if you add more and more, then the overhead of managing them will go up for the hardware. And that means more hardware, that means more power consumption, more area, and so on and so forth, and potentially a slower processor. Okay, so I'm going to jump on this. The fourth operating system concept is dual mode operation. What that means is that the hardware is going to provide at least 2 modes for execution. One is the kernel mode or supervisor mode or protected mode, which we will usually run our kernel code under this mode. And then you have the user mode. This is less privileged mode. It's less restricted mode of execution. So we usually run our threads, our user space threads under this mode. And again, this is provided by hardware. So what exactly should hardware provide to support dual mode operation? Well, simply you need a single bit somewhere that the operating system has to set. Let's say if you only want dual mode. So if the bit is set to, let's say 1, it means that it's kernel code, so it has privilege. It can run anything. And if it is set to 0, then it probably means it's the user code, for example. So it has restricted execution accesses. So what that exactly mean or translate to is certain operations and actions are only permitted when that bit is set to 1 or whatever convention you use. So if you're in kernel mode, you can run those certain operations, and if you're in user mode, you cannot. So users. So when there is a translation, when there is a, let's say, timer expires, the hardware has to set this bit. So if you were running, let's say, your user code, and now you want to go and use the start running kernel to, if it was an interrupt, you want to take care of that interrupt, the hardware sets that bit to 1 and start running kernel code. And then when the kernel wants to go back to user, the kernel has to set that bit again back to 0 so that the user code can execute. So there are three types of mode transfer. So the first one is interrupt. This is an external and asynchronous event that would trigger context switching. For example, the timer could expire. I/O devices could interrupt. Let's say a packet has come, a network packet, and then the NIC will interrupt. So this is the first one. The second one is system call. So these are the ones that the user code will call for a service or ask for a service from the operating system. So the process requests something, let's say exit, or open the file, or read from a file, or get a network packet for me. So all of those, these are system calls. They would actually initiate a mode transfer. And the third one is basically trap or exceptions. So something, let's say you divide by 0, that was not permitted. So the hardware raises an exception, and that exception transfers mode back to the OS. Operating system wakes up to see what to do next. So all three of them are unprogrammed control transfer. So the programmer haven't coded what should happen if any of these happens. So the way to deal with these happens inside the kernel, out of the programmer's control. But it has to be transparent actually to the programmer, to the program. Now let's talk about interrupt. So the question is, if it is not programmed, so if the programmer hasn't coded what should happen if an interrupt happens, like when you write a code, you don't code what happens if timer interrupt happens, right? So operating system has done that. But what should happen when you're basically jumping from what you were running to something else? Usually the way it's implemented is by interrupt vector, for instance, for interrupts. So let's say you were running a code and an interrupt happened. The processor looks at its register. It has a specific register that points to the interrupt vector table. And then looking at what kind of interrupt has happened, it just indexes into this table and goes where it has to go. Who sets these registers? Who basically fills these tables? Operating system. So when the operating system starts running one process, it also sets all the registers that are necessary. This is one of those registers that the operating system sets. It sets the processor's register that would point to the interrupt vector table. And also all those entries inside the table that they also have to be filled by the operating system, because the operating system is the one that is implementing them. Okay. See how much time I left. 10 more minutes. Okay. Now, the operating system, sorry, the hardware could potentially mask interrupts from happening. You could basically be desensitive. You block a certain interrupt from happening. You mask it. So you have an interrupt controller. Here you can see. So your interrupt controller has different lanes that are connected to different devices. And then you can mask them. You can say, oh, at this point, for instance, I don't want to be interrupted by this device. I only want to be interrupted by, let's say, device 2 and device 3, but I don't want to be interrupted by any of the other devices. And then you have some sort of priority selection between the interrupts that has happened at the same time. You will choose which interrupt to access, to process. So there is one lane, though, I think it's not in this picture, that you cannot mask. So there is always this non-maskable interrupt lane or line that you have that nobody can disable it. The other thing to note is that who can disable interrupts? Disabling interrupts is an operation that could only be permitted if you're in the kernel mode. So the user cannot disable interrupts. This is a privileged instruction to run. So this is something to keep in mind. So again, one of the places that you want to disable interrupts is when you're taking care of one. So when the interrupt handler starts running, you have to disable interrupts. You don't want to get more interrupts. So in the classes we've had, I would always pause here and ask why you would want to disable interrupts when you're inside the interrupt handler. But because here it's not that practical to do this, I'm going to answer the question right away. The reason is because you could end up getting interrupted again and again and again and again, and not get out of your interrupt handler at all. So let's say the first interrupt was a very important interrupt. You were dealing with it. A less important interrupt happened, and now you interrupt that interrupt handler to process this other interrupt, and then another interrupt happens and another interrupt happens. You don't want this to happen. So one potential side effect of you letting this happen, other than missing the deadlines for getting the previous interrupts handled, is that you could actually have a stack overflow. So the stack that operating system provides to the interrupt handler, if you let it just be called again and again and again, you're going to push on the stack, push on the stack, push on the stack, and then at some point it's going to overflow. So I got two questions. When in the program execution does the processor check if an interrupt has occurred? Is it scheduled? Okay, so basically at any cycle, the processor is checking the interrupt handler. So if interrupt lanes. So if an interrupt happens immediately at the same cycle that it has happened, the processor will be informed. It's just one bit set to 1, right? That would tell the processor that an interrupt has happened, and then it has to take care of it. So you could have nested interrupt forever then. Yes, exactly. So the downside of not disabling interrupts is that you could have a nested interrupts forever. And once you're done with the interrupt, you enable them and move on. Yeah, these are the examples to disable interrupts, to enable interrupts. Again, I'm gonna emphasize, to execute these instructions, you have to be in the kernel mode. You cannot be a user process and execute these instructions. Okay, how much time do I have left? 5 more minutes. I'm gonna skip answering that question. Maybe I should. So is the interrupt handler a process or part of the OS? This is a really good question. A bit confused about this, or is the interrupt handler implemented as hardware? I will answer that question in details. So short answer, no. Interrupt handlers are not processes. Interrupt handlers are not tasks or threads, and we'll see why shortly. What if more servicing? Oh, what if you're servicing a slow interrupt and you get a super high priority one? I'll answer that question as well later. So we will divide interrupt handling into and doesn't take much time, and it would usually wake up another thread to get it handled. So the first piece that will be run will be executed is very short for all interrupts. That's how we can actually get the priorities as well done. Again, we'll talk about it. Okay, so let's see how kernel system call handler happens. Well, the same way that you did interrupt handling, you do system call handling. So you should have a well-defined entry point for each system call. When a system call happens, the operating system locates the arguments for that system call, which are in user stack, right? So if you wanted to open a file, you have given the operating system the address to that file. You have given operating systems some other information. Let's say I want to open it as write protected or just read only, whatever permission you wanted it. So all of those information are in your stack, inside the user stack. Now you call into the kernel to do the service for you. The operating system has to copy those arguments to its own stack first, and then check them again. So the reason we don't check the arguments in the user space and then copy them is because you could check them there and everything is fine. Before you copy them back, before operating system copies them into its memory, maybe another thread from that process will alter them. And when you copy, you have copied something that is faulty. So the safest way is for you to copy them inside kernel memory, check them in the memory inside your memory, because now that the data is in your memory, nobody else can alter. So you can check them now, validate the information, then call the code that needs to be called, talk to the device driver, let's say, if you want to read a file from the disk. And then once the data is ready, copy the data back to the user process, and then put the process in the ready queue. Whenever its turn comes, it has its data ready, and it can continue running. Okay. I guess I have only 1 minute left. Yeah, I'm going to stop here. This is going to be a little bit too much to go at this point. With that, I'm going to end this lecture. Thank you for those who attended, and we'll continue on Monday from here. Thank you. Bye. Take care. Be safe.